Hello, and welcome to Differential Equations. This is Lecture 3, Slope Fields. Last time, we talked about separable equations. Right, so briefly, if dy dt is equal to f of y times g of t, then either f is equal to 0 or the integral of dy divided by f of y is equal to the integral of g of t dt, and let's go ahead and put the plus c to emphasize it. Right, so those are some of the simplest differential equations that you can just solve right away. This time, we're going to talk about the geometry of first order differential equations. Okay, so when you have any first order differential equation, then you can interpret it geometrically pretty easily. So to interpret an equation like dy dt equals f of y comma t, geometrically, recall that the derivative of a function gives us the slope of the tangent line to the graph of the function. So at each point, e comma y, the slope of the solution curve that passes through that point is exactly given by this function f. This suggests a useful way of approximating, or rather of graphing, approximate solution curves. What you do is at each point in the plane, we draw a short segment with slope given by the function f. The collection of these segments is called a slope field. Or, closely related, a vector field. Then by following these segments, we get an idea of the behavior of solutions to the equation. Okay, so for example, right, last time we saw that if you have the differential equation dy by dt is equal to t over y, then the solution curves are given by y squared minus t squared is equal to c for some arbitrary constant c. Right, so in this case, we already know what the solutions are. You don't need to know the solutions to work out the slope field. Let's look at what it is in this case. Okay, so let's give ourselves coordinate plane, t-axis, and a y-axis. So what we're supposed to do is we look at each point t comma y, and then we look at what the slope is supposed to be there, right? So t over y, and then we draw a small segment at that slope. So, okay, let's start with thinking about if t is equal to y, then this quotient is going to be 1, right? So on this line, our segments are just going to have slope 1. If t is equal to minus y, then the segments all have slope minus 1, right? If t is equal to 0, then the segments all have slope 0. If y is equal to 0, then the segments, well, it's not quite defined, but they want to have infinite slope, so we draw a segment going straight up and down. Right, and if you're on, say, the line y equals 1/2 t, then the slope would be equal to 2, right? So over here, we'd have this slope 2. Right, and over here, we'd have slope 1/2. Right, and similarly, you can fill this in. Right. In this case, we actually know already what the solution curves are. And so we can go ahead and fill in that over here, you'd have something like this, say. Right, so you'd have these hyperbolas. And you can see that if you had a solution curve over here, you'd have something like this. Right, and so on. Let's modify this example slightly and work out another one. So let's consider the slope field of the equation dy by dt equals minus t over y. Okay, so again, let's give ourselves a plane. Okay, so again, let's think about the easiest cases. So here again, if t is equal to 0, then we'd have slope 0. Right, and if y is equal to 0, we'd have infinite slope. Right, notice that this is really not defined at the origin, so we'll just leave that blank. If we're on the line on the diagonal t equal to y, then here we'd have slope -1, right? So like that. Whereas if you're on the anti-diagonal, y equals minus t, then the slope would be 1. Right, and then you could fill in interpolating in between. Right, and so we see here that the solution curves look like they're going to be circles. Right, let's actually work out what the solutions are here. Right, so this equation is separable. Right, so we can rewrite it in terms of differential forms as saying y dy is equal to minus t dt, and then we can integrate both sides. We'd get 1/2 of y squared is equal to minus 1/2 of t squared plus a constant, right? And so we see that our family of solution curves is y squared plus t squared is equal to 2c, right? With c arbitrary. And indeed, we see that the solution curves are circles. Okay, let's work out another example. Let's consider the equation. Let's take an easy one. Dy by dt is equal to y, right? So we know the solutions here are y is equal to a constant times e to the t, right? And let's look at what the slope field looks like. Okay, so give ourselves t-axis and y-axis. Okay, so here the equation looks like this. The slope is just going to depend on the y value, right? So when y is equal to 0, we have perfectly horizontal segments. When y is equal to 1, we have slope 1. When y is equal to -1, we'd have slope -1, right? These are all supposed to be parallel. Right, if y is small, the slope is small. If y is larger, the slope is larger. Right, and that's mirrored on the other side of the axis. And so, as we've already noticed, the solution curves are exponentials and look like that. Okay. Next example. The slope field of dy by dt is equal to y times t. Okay. t, here's y. Okay, so let's think about this. If y is equal to 0 or t is equal to 0, we get 0 on the right-hand side here. So that means that our segments would be horizontal, right? If y and t are both equal to each other, then we get y squared. So on the diagonal, the slopes grow with the height, right? So so we'd have a small slope, and then a larger slope, and then a larger slope, right? And here it's the same but negative. So small slope, and then a larger slope, and then a larger, and then a larger negative, so on. If y is equal to minus t, it's very similar. So is larger, 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 right? Larger, larger, larger. Notice that if you're in the first quadrant, right, y and t are both positive, then this is positive, so we're going to have increasing slopes. In the second quadrant, y and t, y is positive, t is negative, so this would be negative, so you'd have decreasing, right? Here you'd have increasing, and here you'd have decreasing, right? And you can see that basically you just now interpolate between what we've already drawn. Right? And if we go ahead and fill in our approximation, it looks like it might be some sort of parabola, right? This is a simple enough equation that we can go ahead and work out what the solution is, right? So again, this equation is separable. So we can write it in differential form notation. Let's see, we'd say either y is equal to 0 or dy over y is equal to t dt, right? Okay, so we have this solution. Let's consider the remaining case. We integrate both sides. On the left-hand side, I would get natural log of absolute value of y. On the right-hand side, I would get 1/2 t squared plus a constant. Let's call this constant a. Okay, so we can keep going, right? If y is not equal to 0, then I can exponentiate both sides and get that the absolute value of y is equal to e to the 1/2 t squared plus a, right? So that's e to the a times e to the 1/2 t squared. And then y is equal to plus or minus e to the a, e to the 1/2 t squared, right? And then we could call this constant b. So this would be b e to the 1/2 t squared. And here b is arbitrary but not equal to 0, right? Because it came from, it's either plus or minus an exponential, and an exponential is never equal to 0. So this b is arbitrary but not equal to 0. However, if it were equal to 0, then we would just get this solution. So altogether, y is equal to some constant e to the 1/2 t squared with c arbitrary. Okay, so we see it isn't actually a parabola, but it does behave like a parabola. It's actually an exponential of a square, right? So it's growing much faster than a parabola. But you can see from this example that what you get from slope fields is some sort of qualitative knowledge of the behavior of your solution. You don't get necessarily an exact solution. In fact, slope field will never give you an exact solution, but it tells you how the solutions behave. Let's work out one more. So this is an equation we've already considered, the logistic equation, right, from population growth, for example. So this is a first order nonlinear equation with two parameters, k naught and p naught. Right, p naught is the carrying capacity, k naught is some sort of growth rate. And we solved this last time. We saw that the solution is p naught divided by 1 plus some arbitrary constant times e to the minus k naught times p naught t, or y is equal to 0. Okay, so to consider the slope field, let's pick some constants. So concretely, let's consider, say, dy dt equals 4 times y times 1 minus y. Right, so carrying capacity of 1. Okay, now from the context of the problem, if you want to think about population growth, then it makes sense for y to be non-negative. So let's consider the slope field. But focus on y being non-negative. Here's the y-axis, here's the t-axis. Okay, so we want to draw the slopes. Let's stare at the right-hand side. And we see that the right-hand side is equal to 0 when y is equal to 0 or when y is equal to 1. So let's go ahead and draw those slopes. Okay, and then what's happening otherwise? Well, let's think about the sign, right? So if y is positive, then this term is positive. And if y is less than 1, then this term will be positive. So here, we're going to see positive slopes, whereas elsewhere, either above or below, you would see negative slopes. Okay, so it's going to be positive. Let's see, if y is right in the middle here, let's say y is equal to 1/2, then this would be 1/2, this would be 1/2, multiply them together, you get 1/4, multiply by 4, you get 1. So right in the middle, we're going to have slope equal to 1. Right? Below that, the slope is going to be growing between 0 and 1. Right? So we're going to have small slope here growing towards 1. Right? Then after that, it's going to get to 1 and then go from 1 down to 0. So we're going to have something like this. And then smaller. Okay, so then, and above this, we would have small slope going down. Okay, so what do the solution curves look like? They grow until we get to here, fastest growth, and then they slow. Right, so this sort of behavior is used a lot in modeling. Let's write down some of our observations. Right, the slope is positive if y is in between 0 and 1 and negative otherwise. So if the population exceeds the carrying capacity, it will decrease. And if the population is less than the carrying capacity, increase. Also notice that the let's say, also notice slow increase in growth. At the beginning, right, fast growth rate, approaching the peak, right, which happens at precisely 1/2 of the carrying capacity. And then again, slow increase in growth. Right? And notice that all of these observations we made from the equation itself, even though in this case, we do happen to know a formula for the solution. We didn't need to use that formula to make these observations, just the equation itself and trying to draw the slope field, we get this qualitative behavior. In some situations, we don't have a way of observing the carrying capacity directly, right? But we can measure P prime of t, the change in the population, right? So suppose you're measuring some rate of change of some population. If this function behaves like concave parabola, right? So if it looks something like that, then we can model E using the logistic equation, which would then tell us that the maximum of P prime of t occurs when the population is at 1/2 of the carrying capacity, right? So, for example, this is used with P of T equal to the amount of oil extracted from the earth. So P prime of T would be the amount of oil currently being pumped out. Right? So this is a situation where this is something that can be observed, but we don't know what the carrying capacity is. We don't know how much oil there is total underground. So we can try to estimate the total amount of oil by using the logistic model for the total amount of oil extracted, right? In this case, we say we've reached peak oil. When the maximum rate of oil production is reached. Right? How would we know if it's maximum? Well, again, the logistic model assumes that the derivative function behaves like a concave parabola. So we can keep an eye on oil production, and if it looks like a concave parabola and we get to the maximum, then that's when we would say, based on this model, that we have reached peak oil. And this model predicts that that is when half of all of the oil on Earth has been extracted. Right? Another setting where this model is used, right, beyond just population dynamics like we talked about last class, is epidemiology. Yeah, and there, what you're trying to do is predict disease trends, right? So if you want to Google logistic model pandemics, you'll find a lot of papers on modeling COVID-19 using the logistic model. Okay, so those are some examples of slope fields. As a closing thought on slope fields, is that we can turn things around and use this idea to prove that differential equations have solutions. Okay? So what we can do is let's think of our first order equation dy dt equals f of y comma t. As describing a trajectory and let's fix some small unit of time right? Call it tau. And an initial condition, right? Let's say that y of t naught is equal to y naught, right? So what we can do is construct an approximate trajectory by starting at the point, right, t naught comma y naught, right? Because we're assuming that we're looking for the solution that goes through this point. So let's start at that point and advancing along the line with slope equal to f of y naught t naught. Right? So if you were to just advance along that line for a time tau, then you would end up at the point t naught plus tau, and then y naught plus tau times f of y naught t naught. Right? Okay, call this point t1 comma y1, and then repeat this procedure to find a point t2 comma y2, right? And so on. Right? In this way, we have an approximate solution to our initial value problem. And then by making tau smaller and smaller, we get better and better approximations until eventually, if everything goes well, we converge to a solution.